Today we present you AdaRadar, Rate Adaptive Spectral Compression for Radar-Based Perception. My name is Jinho Park from Columbia University, advised by Professor Mingoo Seok. This is joint work with Professor Chun of Seoul National University. This is the table of contents. I'll talk about motivation, proposed methods, experimental results, and end it with a conclusion. The motivation. So radar perception is a critical sensing modality in autonomous driving pipelines, as this complements camera and LiDAR. And this is because radar is robust to lighting and weather conditions. It also has unique ability to measure relative velocity and range. However, this poses bottleneck on the link bandwidth. Unlike a camera, which only has 3 channels, RGB, radar sensors have quadratically scaling channels to receiver and transmitter antennas. So for example, a single frame from a 16 by 12 cascaded MIMO radar system configured with 512 range bins and 256 Doppler bins amounts to roughly 100 megabytes per frame. And also the radar codecs, coder encoders to compress these radars are quite absent. So natural images span a broad dynamic range, as you can see from the figure on the left. On the figure on the right, you see radar signals exhibit extreme sparsity and a heavy-tailed profile. And this necessitates specialized compression beyond standard image domain codecs. So I'll go over the proposed methods. So our proposed method introduces a feedback loop in which the proxy gradient is computed from the detection outputs to update the compression ratio adaptively. This avoids the need for backpropagation through the communication channel. It involves DCT-based compression on the radar sensor side and decompression on the compute side. And the motivation, a motivating example is the DCT coefficient's magnitude when we picture on the left are clustered in the high frequency bands, and also its histogram on the right is sharply picked. So it highlights the strong sparsity, and clear opportunities for compression. Adaptive compression includes spectral pruning and symmetric quantization as a result. So this figure shows the original and reconstructed range and Doppler maps from a single channel. And we also show the magnified 64 by 64 patches at different pruning ratios, and also the SNR versus bitrate roll-off. And the reason why we use a pseudo proxy is that labels are not available at test time and to model the performance of the network. And however, we do have the bounding boxes in the object detection with its respective probabilities. So we use those confidences as the surrogate objective. And we also show you this B-box confidence with a great correlation with the ground truth labels. And although we don't have it at the test time, but if you were to picture it, we see a high correlation. And also the test objective here, we use H, which encapsulates compression, decompression, forward inference, and B-box proposal, and also a hyperparameter lambda and an instantaneous bit rate. And we take a gradient with respect to R, and we perform and calculate the proxy gradient from 2-4 passes. And we also delineate the algorithm here. And in sum, it computes a gradient with only 2-4 passes. And we now show you the experimental results. Camera images provide contextual reference for the scene, which is obviously not fed into the network because it's a radar-only task. The network predicts both detection and segmentation outputs, and compressed range Doppler map leads to improved performance compared to the uncompressed baseline. And we show you the rate accuracy trade-off. And our compression scheme achieves 100 times reduction in the radar feature size while having only a 1 percentage point decrease in the performance compared to the baseline. And against Pixar, our method achieves better precision and markedly better recall. And against a index value based method, the compression selects top key elements in each m by m block according to the energy value at the spatial domain. And our method remains stable until 5x compression, whereas the performance drop in the other method, and the index value based method, drops immediately. And the roll-off gradient of 23% over a decade is much more gentle for our case than 46 percentage point for the index value-based counterpart. And we also show you the effective quantization bit width on detection, and we observe that up to 4 bits does not affect the performance compared to 8-bit and 16 bits. And we use the FFT RadNet on the radar dataset without any fine-tuning with block length of m equal 64 for all cases. And we also examine the effect of varying block sizes on compression on the radar dataset. And we show that the average precision recall and F1 score degrade across block sizes for M with 4-bit quantization with the same setting. And we also visualize the online compression with bitrate and detection metric. And it is expected that the controller decreases the pruning ratio to compensate for the average recall drop. And it achieves an average bitrate of 0.279 bits per pixel with 8-bit quantization, and in total yielding a 115 times compression with AR of 93.9%. And we show you the holistic performance on the radar dataset, and an average pruning ratio of 12.57 times combined with 8 times gain from quantization yields a bit rate of 0.32 bits per pixel, corresponding to a 101 times compression ratio. And on segmentation task, ours actually improved the performance, and our method markedly surpasses the index value-based method. And on Carrot dataset, it allows an even greater compression ratio of 117 times while maintaining the target metric close to the non-compressed baseline with 1 percentage point drop. And on Radartron dataset, a range azimuth heat map is compressed and by up to 30 times. And even at this compression ratio, our method actually provides better performance than the non-compressed baseline, up to 5 percentage point improvement on average precision 75. And in conclusion, we present AdaRadar, a rate-adaptive spectral compression framework for radar-based perception. A pruning and quantizing DCT coefficients shrink the range Doppler cube by over 100 times, easing the sensor to compute bandwidth bottleneck while preserving accuracy at the lowest bit rate target. A lightweight test timing controller finally adjusts the compression ratio on the fly. It makes a judicious trade-off between bandwidth and performance in real time. And thank you for listening to AdaRadar.